This video is going to be hopefully pretty short. I wanted to take you through how working with improper integrals actually works. Hopefully, you should have already watched the video that explained what they were and what made them improper and how we adjust them. But now I want you to see some in action. So this is going to focus on 4 examples, all of them that have the same issue. It's the most common issue, which is what do we do when you have an upper boundary that's an infinite boundary instead of a finite number? So the checklist here, this is a nice thing to kind of make note of. This is how you're going to attack every single problem, no matter what type of improper integral it is. First step is you want to set up the correct limit notation. It is so easy to just neglect to do that. If it's a free response question on an AP test, if you don't write the correct limit notation, they won't give you full credit. On the flip side, if you write the correct limit notation and then have absolutely no idea what to do, you still get a point. Once you do that, then you're going to integrate what you have left using any rule that we've learned to this point, which so you have a lot of options. Once you do that, you'll evaluate the limit. So see what happens as you take the limit as it goes to infinity or negative infinity or a particular value. And then when it's all said and done, it will often ask you to describe or label. And when they're asking you to describe or label, a converging means that you get some sort of number, any number, positive, negative, zero, and diverging means you get an infinite value. Also easy to forget that last step, even though it's a very easy step. So for all of these, my adjustment, my limit notation is going to be what happens as we go towards infinity. I'm going to use the letter B since all of these have my infinite value as the upper boundary. So this is how they're going to start. I actually do both of these side by side the same way just to kind of get the basis going here. So you're going to go from 0 to B. You can use any letter you want for that upper boundary. Use a letter that hasn't been used yet. So for example, don't use X, don't use E, don't use L because it looks strange, but try to pick a letter. Again, A's, B's, and C's are pretty safe. So for this one here on the left, I want to integrate 1 over X. That is a natural log integration. So here's what it looks like when I integrate. When I put my boundaries in, so this is a fundamental theorem, I get the natural log of B minus the natural log of 1. I am carrying this limit down the whole time, although I do tend to get a little lazy with that. The natural log of 1 is 0, so I'm going to cross that off. So now I'm left with the natural log of B. So now I'm ready to evaluate the limit and figure out what happens to the natural log as we get bigger and bigger values. Well, you should have an idea what natural log looks like, just a real general sketch. This is natural log, just a real simple sketch. As I go towards infinity, my graph is actually going bigger and bigger. It's very slow. It's one of the most gradually growing graphs we have, but it is still getting bigger. So we end up getting a limit that evaluates to an infinite value. What that means is this is a diverging improper integral, and feel free to abbreviate DIV and CONV for those descriptions. For the second one, so I have an integral that's e to the negative x. I'm going to do a little u sub off to the side. You may be able to do this without writing all this, and that's fine, but I don't like to skip steps when I'm explaining. So if I let u be the negative x, the exponent derivative is -1, so I have a negative adjustment. And I'm integrating e to the u, which gives me e to the u, so I get negative e to the negative x. When I evaluate this limit, it may be easier to think of it as it part of the denominator. Just because of negative exponent, that's what that means, and sometimes evaluating limit when you don't have negative exponents is easier. So when we put our boundaries in, we get -1 e to the b minus a minus, so plus 1 e to the 0. E to the 0 is 1. So I end up getting a plus 1. So now I need to figure out, so this is equal to 1, what happens as I go to infinity for b in this first part. So what happens with that? As you put an infinite value in for the exponent of e, it's going to get really large. As I take any number and divide it by something really, really large, this whole limit is going to go to 0. So in the end, what you have is you have a limit that evaluates to just 1, because that is what is left here with this constant piece. So we would say that it converges. Here's what you're actually doing in kind of like the application of it. In the first one, because we got a diverging, what this says is if you look at the area under the curve of 1 over x, it's just going to continue to get bigger and bigger and bigger as I go to infinity. As you look at the area under the curve of e to the negative x, as we go towards infinity, your area tends to like level off and goes to a value of 1. So just to give you an idea what your number, your answer means in terms of area and integration. 2 more. Both of these, again, having the same issue. So we're going to take the limit as my upper boundary is going to infinity. And same thing over here. When you're on an AP test, you just have to promise me not only you'll write this integral at the beginning, but they do expect that you write it over and over again. I'm going to rewrite this one also while I'm going. This is x to the negative 1/4 because it's in the bottom. So while I'm rewriting, I'm just going to do both of those things in one step. So this first one on the left, I need to figure out how to integrate 1 over x squared plus 1. Hopefully that looks familiar as one of our integrals that we reviewed earlier in the chapter. This is an inverse trig. This is arctangent. It can't be done as a u sub. It is the simplest arctangent though. Your u is x because that's what was squared to get the x squared. Your du is just dx, so no adjustment. Your a is 1. So it is just the arctangent of x over 1, or the arctangent of x, as we go from 0 to b. So you get the arctangent of b minus the arctangent of 0. And now we're going to look at what happens as I take that limit. You should know the inverse tangent of 0 is 0, because tangent of 0 is 0. It kind of goes together. Arctangent is probably not one you're really, really comfortable with as far as visual. You should be comfortable with what natural log looks like. You should be comfortable with what e looks like. Arctangent's probably not there. So I actually included this picture. If you started this and wondered why did she put that picture, that is actually a picture of arctangent. Arctangent has 2 horizontal asymptotes. For some reason, only one's drawn in. Arctangent flattens out. So what you have happening is you have a horizontal asymptote on the far right end, or on above it, and a horizontal asymptote below it that kind of makes the right end go one direction and the left end go the other. Both of them will flatten out towards pi over 2. So what this means is, and you can see arctangent of 0 is 0 because of the origin being there. I hate when it does that, sorry. So that's 0. The arctangent, as I go towards positive infinity, so that's going this way towards positive infinity, it is going to have a limit of pi over 2 because it flattens out to pi over 2. I don't expect that you knew that graph before you started this video, but it is something that you want to kind of take a look at and get comfortable with. So because we get a finite number, it converges. And then finally, the last one. This one is just a basic power rule. So power 1 greater, so the 4 is going to stay here. Power 1 greater than negative 1/4 is 3/4. So power 1 greater divided by that power. Put my boundaries in. So I get 16/3. This should be a b, not an infinity, sorry. B to the 3/4 minus 16/3, 1 to the 3/4. 1 to the 3/4 is 1 times 16/3. This part is just going to be 16/3. Now we want to see what happens as I go towards infinity and take that, put that right here. Any an infinite value, if I'm taking it to a power, if I take infinity to the 3/4 power, it's going to get bigger and bigger and bigger. So this whole thing is going to become infinite. I then take off the 16/3, which does really nothing against the infinity. Infinity always wins. So I get an infinite value. And what that tells me is that this one diverges. So there's some examples of improper integrals in the most common situation. The most common situation is that infinite upper boundary. We'll look at other examples of what happens if you have negative infinity on the bottom, what happens if you have a discontinuity, but I wanted to start it with this video.